So in this example, we are given dx, we are given x in terms of t here, right? Or in our case, it's theta. Then we find that dx over d theta is r times 1 minus cosine theta here. Dy over d theta is r sine theta here. Then applying the theorem 5 here, we have that the curve went from t is equal to 0 to 2 pi is given by this formula. Substitute dx over d theta to this formula and dy over d theta, we have this equation. This is a perfect square, right? Which will be 1 minus 2 cosine theta times 1 plus cosine square. And all the other terms here, we have the common like term, r squared. So we factor it out. That is why we have this, guys. Okay? Now, let us continue. Jonathan? So here, let us simplify it. First, cosine square plus sine square equal to, yes, 1. So now here is square root of r squared times something else. So we can write it as square root of r squared times square root of the other guys, right? And here 1, we just rewrite it, minus 2 cosine theta. This guy is 1. Very well. Okay. So what should we do now? Yes, square root of r give us r, and we take it out of the integral, right? Because we're integrating with respect to theta. So r is simply a constant. Makes sense. So we write r here. And this integral becomes this guy, 2 plus 1 plus 1 here give us 2, right? Okay. So at this point, what should we do? 2 and 2 is a like term, so how can we solve it? Yes, let us factor 2 out and see what happens, right? Then it will be square root of 2 times 1 minus cosine theta here, right? D theta, okay? And now we're stuck. So we need to use somehow manipulate this guy. Let us rewrite it here. This is r integral from 0 to 2 pi. Square root of 2 here, we just take it out, right? This guy is 1 minus cosine theta d theta, okay? Do you have any idea what we can do with this guy? Yeah, that's what we should do. And take a look at the reference formula that gave you about trigonometry and tell me which formula we should use here in your point of view. So which formula do you think? Now look at this. What do you think about these two formulas? So here, this guy looks somehow similar to our terms here, right? The angle is different. But anyway, if we're given here from this relation, what does it mean? It means that 2 times sine square theta, very good. 2 times sine square theta will be very well. Or in general. So if we replace it by 2, it means this is true for any angle, right? We just use a different notation. Do you agree? They're the same things, right? Use different names. If now here theta is equal to 2x, okay, then the right hand side we have that it would be 1 minus cosine of yes, here if theta is 2x, then theta over 2 will be x here, right? Therefore, the left-hand side becomes sine square of theta over 2 squared here, right? Very good. It means that we can rewrite this terms as this guy, okay? Is it clear? Yes, let us rewrite it first. Therefore, we plug it in here. We have r 0 to 2 pi square root of 2 times. Here it would be 2 sine square of theta over 2 t theta, or let us write it this way. Yeah, square root of 2 of the whole things here. Okay. Now let me remove these guys. Here, the inside here with 2 square, right? Therefore, we can take it out of the radical sign here. Right? It would be 2. And here, look at this. It is square root of sine square theta over 2 d theta. Okay? So remember, when we take a square root of x squared here, what do we have? Absolute value of x, right? Yeah. Therefore, this will be the absolute values of Very good. Let us take the 2 outside and square root of sine square of theta over 2 d theta. Now, the absolute signs here is annoying, right? So we want to get rid of this. Before doing, oh yeah, just sign here. Sorry. Thank you. So now, how can we get rid of the absolute sign here? Very good. Thank you, Walid. It's a great observation. Here, look at this. When theta is larger or equal to 0, smaller than 2 pi, right? It means that theta over 2 will be larger than 0 and smaller than pi. And here is the unit circle. The angle is from 0 to pi. We know that sine of that angle will be always positive, right? If this guy is always positive, then we can get rid of the absolute sign perfectly well. So, very good. Therefore, it will be 2 r integral from 0 to 2 pi of sine of theta over 2 d theta here, right? Now we do substitution, right? Do substitution, or because you do many integration already, let us quickly write the result of this. What is antiderivative of this guy? Negative cosine, and remember, when we take derivative, the chain rule, we need to take derivative of this guy, right? It will somehow appear a term 1/2. Therefore, we should have twice of this, okay? Do you agree? And it is a definite integral. So we take the value from 0 to 2 pi here. Okay? Therefore, it will be let us take 2 out, and it will be 4r, right? It will be 4r times, we substitute the upper limit. It will be negative cosine of, yes, and minus the negative of, very good. It will be cosine, this will be cosine of pi, right? Cosine of pi, which will be -1. And this guy, oh, negative and negative, yes. Here, right? And here it will be cosine of 0 will be 1, negative, negative. Okay. Very good. So that's it for this one, right? Are we good? Then
I have a question. Why did the 1 from the negative cosine of 2 pi over 2 become positive?
Wait me a second. Let me volume up a little bit. Interesting. Carrington, can you say it again?
Yeah, the first one that's from negative cosine of 2 pi over 2, why did it become positive?
So cosine of 2 pi over 2 becomes cosine of pi, right? And cosine of pi will be -1. And in front of that, there is a negative sign. So negative of -1 gives us 1.
Okay,
Okay,
thank you.
is it clear now?
Yes, it's clear.
Okay, thank you. Everyone else? Then now that is one example for that problems. Now let us move on to another idea, the surface area. Suppose, look at this. The parametric equations of this is given by x is equal to fx and y is equal to ft and y is equal to gt. T is from alpha to beta. Look at this. If the curve of this parametric equation is given by this one, like this one, for example here, when t is equal to alpha and t is equal to beta, from this to this, we want to compute the surface area of this curve, which is rotated by about the x-axis like this, right? When we rotate this about the x-axis, it will create a surface. And the question is, how can we compute that surface? And remember, when we rotate it, then this point here, this guy here will create a circle like this one. Okay. And here, this one is right here. When we rotate it, it will create this circle. And the surface we are computing, can you imagine it? Okay, just here. Look at this. Here is the y of t curves, right? This is the curve y of t, right? This blue line. So the surface area of this object will be the sums of each circles here at each point, right? See it? For example, right here, it will be this circle. Okay? And suppose if we cut this, look at this circle, the biggest circle here, if we cut it and stretch it out to becomes a line here, how long is it? How long is this line? This one. It is a circle, right? With the radius is y of b, and yes, it is 2 pi r, right? Where r is the radius of this circle. In this case, it will be y at b, right? You agree? So we have this 2 pi y here, or in general, let us write, yeah, just write it in term y at this point. So if b here, the point here, or it runs this point, the same things, it will be y at a here, right? If the smaller circle here. If this point run from this to here, right? It will create a ds. This is the ds, right? Where s is the curve here. So you see it? It means that, and remember, ds is square root of dx squared is this guy. Okay. Now, if we take integral from this to this, it will be integral from alpha to beta of 2 pi y ds, right? And ds, now we rewrite it in terms of dx over dt squared plus dy over dt squared here and all the radical sign here. That is why we have this formula number 6 here. Okay. You see why we have this formula? Very good. And then let us just use this formula from now. Okay, show that the surface area of a sphere of radius r is this guy, right? So the sphere is obtained by rotating the semicircle here. Here, right? If we rotate this semicircle about the x-axis, right? It will create a sphere. And remember, this circle, semicircle, will follow this here parametric equation. X is equal to r cosine t, y is equal to r sine t, when t is from 0 to pi. Okay, this is r. Do you see it? So, since we have this, we can use the formula 6 in the equation 6. S will be integral from 0 to pi of 2 pi r, right? And y will be r sine. That is why we have this guy right here. And square root of dx over dt. What is dx over dt here? Very good. And what is dy over dt? Very good. R cosine t here. So we substitute it here, right? We have negative sine r, negative r sine t, and here plus r cosine square. Then let us compute it. Okay? From here, we know that the surface area would be the integral. 2 pi r is constant, right? They are constant, so we can take it out of the integral here. Sine t here. And in this guy, when it is square, it becomes r squared sine squared t plus r squared cosine squared t here, right? dt. square of a product will be product of d square, which is this. And look at these terms. What is the like term? R squared. So we factor it out, right? Thank you. So each of you take a drafts of paper and compute it. Let me know what you have. Yeah, take your time to do it yourself. When you do it yourself, you memorize it better. Okay, go home and double check this result yourself. It's a simple integration, so I believe that you can do it yourself. So that is all about the chapter 10.2